Now we're going to move on to chapter 24, which is where we're going to start talking about light as a wave. Thus far, we've been talking about light as a particle because it goes in a straight line. But now we're going to talk about light as a wave and Young's double slit experiment, which was the first real experiment to definitely prove that light was a wave. So light is both a particle and a wave. We know that now. It took a long time to realize that it could be both. So the wave nature of light is needed to explain lots of phenomena, including interference, diffraction, and polarization, all of which we're going to go through in this chapter. And we can see that waves have this behavior where any small part of a wave can make a new wave coming through. So we can see the interference patterns in these water waves, in addition to light waves. So interference, what is interference? Interference is when two waves overlap each other and can either amplify each other or cancel each other out. So if I have two of these red waves, I'm going to get the blue wave, right? Because I have two maximums overlying each other. However, if I combine the red wave and the green wave, I'm going to basically get nothing because those will cancel each other out. So what are the conditions for interference with light in particular? Well, for light, we need to have a source that is coherent. Coherent means that all the waves are lined up with each other. So we can have white light. White light does have interference. It's just really hard to see because it's hard to pick out one color at a time because only one color is typically being interfered with at a time. So the white light is got all the different wavelengths, so we typically don't see the interference there. We have monochromatic light, and monochromatic light could possibly not be coherent in that the waves could all be scattered about as to where their amplitude is at maximum or it's at a minimum. So, and for interference, we must work with waves that all have identical wavelengths. So, and that's going to be typically done with a laser. It was originally done before we invented lasers. If you had a monochromatic light, basically what you did is you shined it on a screen with a very small hole, and then the light going through that very small hole created a new set of waves, and all those waves were then coherent. They were having the same waveform, that they were having the same maximum and minimum locations, and then you could do your experiments with those. The more modern way to do it is with a laser. So all current applications of interference and wave optics use a laser as the light source because the light is in fact not only monochromatic but also coherent.